So at the beginning of my first lecture, I said I was going to make a start with talking about surface codes in this last lecture, but I actually won't be doing that because I do have 2 lectures in Chalmers, and I have a lot of more material that I'd like to discuss before we go into the surface code. And maybe also to reiterate, if you find this topic interesting, and if perhaps I've gone too fast or glossed over a few points, look at my review, because I think I write better than I talk, perhaps. And so many details you can read there and at more, at your own pace. And so I hope you get something out of that. Anyhow, so what we want to do today is start with a little bit of more of a mathematical view of what qubit stabilizer codes are. Then talk about the fault tolerance threshold theorem and concatenation. And then talk a little bit about logic and Clifford group operations. And the reason I do want to spend this time is because I do think that quantum error correction is not a new subject. It's not a very old subject either. But there's a huge literature on it. And of course, I cannot compress this literature in 3 lectures. But I do want you to be aware there is a lot of previous work. And also I'd like you to be a little bit aware of why is the surface code currently the favorite and what would be the alternatives. I cannot barely touch on this. But somebody has to, this is not coming out of the sky. Somebody has to design these coding architectures. And I've tried to work on this in the past and think about this. And this, of course, is sort of specialty by itself. Now, I don't assume that you're all going to be working on this, but I think it is important that this work is done, and it's also important that it's connected to the actual experimental constraints in devices. And I hope that phase of work will be done in the next 10, 20 years, and that you may be contributing to that. Okay, so this is a little bit of a recapturing of things that I've already said, maybe in a formal way. Where's the stick? Let's see, is there a stick? Okay, this is not a stick. Oh no. Do you see? Oh, there's a stick. Yeah. Okay, this general structure of qubit stabilizer codes, and the reason that stabilizer codes are popular is that. For several reasons. So we have these quantum error correction conditions, but in general, it's not so easy to check whether a set of errors it satisfies the quantum error correction conditions. And for qubit stabilizer codes, it's much easier to check what kind of errors the code can correct. Furthermore, it's fairly easy to specify the code subspace. And it's easy to specify what the logical operators are. It's also easy or fairly easy to do certain gates on encoded data, right? So if we want to use a code to do computation with, we encode the data, and then we, in order to do logical gates like a Hadamard transformation or something, we want to do it on the encoded data. Now, how do we do that? So for qubit stabilizer codes, they're fairly simple things that one can show. That constructions that tell you how to do this. And I'll go into some of them today. Okay, so how we get a stabilizer code. So we start with, let's imagine we have n qubits, and there's a group. It doesn't matter that we call it a group. It's just the products of all Pauli operators and all these qubits. Like, for example, this is an example of such a Pauli. X2, the Pauli X on the second qubit, Pauli Z on the third qubit, identity on the nth qubit, etc. And so that's this blue circle P. And now we take a subgroup, which is the red thing, which is abelian. So all the operators in the subgroup, they commute. I said before, in general, Paulis commute or anti-commute. So we have to take some bunch of Paulis that all commute. Now, for example, x1, x2 commutes with z1, z2 because, they twice anti-commute. And this notation with these brackets just notes that this is a group. So I can take the generators of the group, and these are two generators, and that's the group is then called a stabilizer group. And so the code space, so now we specify the generators of the stabilizer group, and with that we can specify the code space. So that's mathematically done like this, and I said before already, it's the +1 eigenspace of the elements in the group S. And because this group is generated by, so it's the +1 eigenspace of the generators of the group. That's sufficient. And I've mentioned these generators also called them parity checks. Okay, so the example is of this group. What is the +1 eigenspace? Turns out it's just this state. It's a one-dimensional eigenspace. It's just the state 0, 0, +1, 1. Now, a general comment about the dimension. So this is a nice property that it's very easy to calculate the dimension of the code space. Okay, so that's this statement. So I have the stabilizer group, and let's assume that it's generated by k linearly independent polys. So k linearly independent parity checks. Then the code space, it's 2 to the n minus k dimensional, encoding n minus k qubits. No? So example, here I have 2 qubits, and there are 2 of these checks, so that makes the code space one-dimensional. Yeah? So it's 2 to the 0 dimensional. So, for example, we'll talk about this code. So the 4-qubit code. Okay, so now we can, with that formula, we could calculate what the dimension is of the code space here. Right? So I have 4 qubits, so that's 2 to the 4 minus 2, so it's 4-dimensional. So 2 qubits. And so the +1 eigenspace specifies a 4-dimensional space, subspace, and so encodes 2 qubits. Now, there are also, so you can ask why this is the case. There are simple arguments that can show this. I won't go into this, but okay, so if you want to know, you can ask me afterwards. So there are also non-stabilizer codes in which there are check operators, and they still commute because they have to have the common eigenspaces, but they're not necessarily Pauli's. There is also formalism of subsystem stabilizer codes, which I will not touch upon, in which I start, instead of with an abelian group, I start with a non-abelian group. So also a subgroup of the Pauli group. And there are some potential advantages and uses of these subsystem codes, but I don't like to go into that because it would take too much time. Okay, so once I've determined the dimension of my code space, so I know how many qubits I encode, I'd like to find their logical operators. Let's imagine I'm encoding n minus k qubits. So I need to find n minus k pairs which represent the logical z and the logical x. Okay, now I think I already went to some of this yesterday, a few days ago. But I just want to reiterate it a little bit in more mathematical formalism. What are the properties that these logical operators? So these two, of course, anti-commute, this pair. Yeah? But the logical operators acting on different logical qubits should commute, right? Because they're different logical qubits. So how we find these operators? Well, what is the property that they need to have? Is they need to commute with all the elements, with all the parity checks. And I think I mentioned that a few days ago. Why do they need to commute? Because they need to map code words onto code words. And code words satisfy parity checks, and that's why they need to commute. So the logical operators commute with all the check operators. But they should not be products of the check operators. Otherwise, they act trivially. No? So if we want to draw this, we have the set S, which is generated by the parity checks. And then there's a set CS. And in CS, there are operators that commute with everything in S, but they don't necessarily commute themselves. And the C of S is called the centralizer. So C of S, which is all the yellow thing, which includes S. So C of S includes S and all the logical operators. Yeah? And I said also the logical operators are not unique. Okay, what else do I have in my poly group? Now, I also have operators that do not commute with all the elements in S. Right? And they are out here. And I also said that those operators I can detect. So I have an error. Well, I have an operator. This is a bit more general. Say I have an error on an encoded state. So there's three possibilities. This error is a poly error. Okay, so first possibility, E commutes with all elements in S. Okay, then I have two further sub-possibility. Either E is trivial, it's an element in S, or it's a logical operator. That's bad, right? Because I won't detect it because it has an element in S, and it's a logical operator. Or it anti-commutes with some elements in S. Yeah, so there is an S such that it anti-commutes, and therefore it's detected by that stabilizer check. So those are the three possibilities. Either E is proportional to a check operator, which is trivial, or it's proportional to a logical operator, or it's detected. Yeah. Okay, so the distance of the code, which I also mentioned, is the minimum weight of the logical operators. And a code can detect all errors of weight less than D, because the minimum weight one, the logical, a logical area. A logical operator has to have minimum weight D or higher. So these guys have to anti-commute with some of the stabilizer checks. Okay, so let's now just see a very simple example. Let me see if I want to, yeah. Okay, so let's look at this guy. I barely need this, but okay. So I said here, this is the 4-qubit code. And let me construct the logical operators. I said I have to find two pairs, right? It encodes 2 qubits. So I have to find a bunch of operators that commute with these two, right? So let me write down one. I'm going to call it Z1, Z2, and I'm going to call it the logical Z1. So this is the logical Z of the first qubit, first encoded qubit. Now I have to find X1. Why does it commute? Because it overlaps on 2 qubits. Yeah? So it anti-commutes twice. Now I have to find X1, and X1 has to be such that it anti-commutes with this guy, but it commutes with everything over here. And it's clear that I can take this to be any even, if it's a product of 2 x's anywhere, it will commute, right? So I could choose to be this one. So that will anti-commute. And similarly for Z2. Okay, so Z2 needs to, this guy needs to commute with this guy. Why? Because it's acting on a different logical qubit. So it can be chosen to be this, Z2, Z3. And X2 can be chosen to be X1, X2. Okay, so these anti-commute, and these again commute. Okay, so that I found logical. Yes? Wait a moment, I did write something wrong. Z1, Z, sorry. Thank you. Yes. Okay, so I found logicals. Now, what is the distance? So I have to look at any one of them and try to minimize its weight, and I'm allowed to multiply with these check operators. Now, of course, you see that these multiplying with this doesn't diminish the weight, So the distance is 2. And the code can detect 1 error. Yeah? So this is the 4-qubit code. So we note this as a 4-2-2 code. It's 4 physical qubits, 2 logical qubits, and its distance is 2. Okay, so now let me give you the argument. Okay, so that's detection, right? So in order to be able to correct error, I need to have a higher distance. And why is it so? So let me show you this. Code with distance d is 2t plus 1 can correct t errors. I like to just to give you, so we talk about t poly errors. Okay, and I think I already gave you a sketch of this kind of reasoning in the previous lecture. And but let me sort of put it together in this sort of slightly more formal way. Okay, so some error happens, E real, and its weight, which is the number of qubits it acts on, is less or equal than t, right? Because that's the kind of error we want to correct. You know? And now we infer an error. And the way we infer an error is we pick the error. So we have a bunch of parity checks which come out +1 or -1. And we pick the error that could be responsible for those parity checks, which has minimum weight. And well, we know there's a real error that has weight less than t, so this inferred error also will have weight less than t, less or equal than t, right? Because it could be the real error, could also be something else. But we at least know if we pick the minimum weight one, we always find something with weight less than or equal to t. Yeah. Okay, now the the real error was responsible for some pattern of parity checks, and the inferred error was responsible for the same pattern of parity checks. And which pattern I got was determined by the anti-commutation. So what that means is that if I take the product of these and look at whether they anti-commute, so Si is an element in S, is a group, it's like a parity check, then I claim that Si will commute with the product. Why? Well, E inferred anti-commute with some of those Si. This is for all I. E infer anti-commuted with some, but E real anti-commuted with the same. Twice anti-commutation is commutation. So this product commutes with all Si. Yeah? Because they both anti-commute with the same guys. Aha. So E real times E infer commutes with S. So what can it be? Then it's an element. So either E real times E infer is in S. It acts trivially on a code word. So this is good. What it means is that if E real happens, then I do E infer, then overall I just do something trivial, so I'm good, I've corrected my error. Or E real times E infer is an element in CS, but not in S. And this is sometimes noted, so not in S. Meaning that it's a logical. So this is meaning that it's a logical operator. So then I say bad. Right? But can this happen, this last case? Okay, so, because I've assumed something about E real and E infer. Okay, so I have to now see whether this case actually happens. Okay, well, my code had distance, D is 2t plus 1. Now let's look at this. This is E real, which has weight at most t. This is E infer, which also has weight at most t. So the product has weight at most 2t. And any logical operator has weight at least 2t plus 1. So this cannot be illogical, right? Which is less than 2t plus 1. Conclusion, cannot be a logical operator. So the conclusion is that, so this is what I want to show. A code with this distance can correct any subset of t errors or less. Because I can apply this argument. And if I just try, if I find any error that was responsible for the parity check bits that I get, that has minimum weight, I will always find either exactly the error that happened or something that is, has the same action on this code space. So I'm good. Yeah, is this argument clear? Okay. What's E-real is a product of polys. It's a poly error, right? So it could be a bit flip on the first qubit, phase flip on the third. Infer. And E infer is the error that I infer. So I get my parity check measurement outcomes, and I'm going to do some classical processing to determine what error I think happened. And that I call E infer. The error that I inferred from my classical, maybe it's a lookup table. And the way I infer that classical error is say I'm going to take the error that has minimum weight, a poly error that has minimum weight, that could be responsible for what data I'm getting in terms of these parity checks. Okay. Okay. So a few more examples. So okay, 4 qubits won't do. So we need to have a code which has distance 3, right? Because then we can only then can we correct one error. Of course, this argument works if you have errors happening anywhere, right? You say I only have errors there, then it's different, right? It's just less restrictive. Okay, so we need to, in order to get a code that corrects a single error, we need to use more qubits. So one can use the Shor code or the Steen code. Now I want to say, yes, I think I already said some of that. So there's a lot of stuff on this slide, which is clearly showing that I'm violating the rules that we learned yesterday. Okay, so I have to give you some time to look at this now. Okay, because that's a lot of junk. Okay, so yeah, so I want to make one comment about the Shor code. Because the Shor code, so the Shor code is a 913 code. So I need 9 physical qubits. In code 1 qubit has distance 3. And I could lay out these qubits in an array of 3 by 3 array where these are the qubits. And I could also view the Shor code as the smallest in a family of codes which are called Bacon Shor codes. And these have parameters n squared 1n. And so this layout is something where n is 4. So it's a slightly bigger one. And I could scale this up also. Now, the Bacon Shor code viewed in a certain way is a subsystem code, and I don't want to get into subsystem code. So I'll mention something about it. But let's look at what the Shor code actually is. So for the Shor code, the check operators are these. So this green thing is a ZZ. So the parity checks are ZZ, 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 ZZ. All the horizontal lines have parity check Z's. And for the Shor code, there's also there's Z checks and there are X checks. And these X checks are what I call double row operators. They are x1, x2, x3, x4, x5, x6. That's one guy. You see his weight 6. And the other guy is x4, x5, x6, x7, x8, x9. So that's also weight 6. Yeah. You can also identify the logical operators. What I want to say about the Shor code is that there is a way of seeing this as subsystem code by which, instead of measuring or handling check operators that have high weight, so these double row operators, if I scale this to the lattice, then they'll become very long, right? There'll be, the idea is that for this lattice, there'll be double row operators which have now weight 8. And if you say, well, I'd maybe like to physically realize such a code, I would prefer to measure check operators that are local and that act on few qubits. So you get the Bacon-Shor code is actually, you can have a modification of this code by which what you measure are weight 2 z checks, which are horizontal links, and weight 2 x checks, which are vertical links. And in that way, it's like the surface code in the sense that the parity checks are very, very local. But you can also show that this Bacon-Shor code, if you take this lattice to be very large, the threshold actually goes to 0. So this is not a good code to use in an asymptotic fashion. But there are other features of this code that are interesting. But it's a subsystem code, and I don't want to go into this. Okay, I think the rest of the slide I actually already said in this board. Okay. Okay, so now. Okay, so we already saw. I think I also mentioned this. So we have to measure these parity checks. Now I want to say something very simple, and maybe you can verify this yourself. So as in the first lecture I said, we have to measure these parity checks. So what is doing error correction? Okay, so first you have to encode a qubit, or say a 0 or a plus, into, you have to encode it. So you have to prepare a logical 0 or 1. Let's see. And then you just have to do error correction all the time. And what does error correction do? You have to measure the parity checks, and based on that information, you have to infer what errors took place, and possibly you have to correct the errors. Or you just keep track of it in classical software, what errors you think have occurred. Yeah. Okay, so how we do measure these parity checks? Now, the parity checks for stabilizer codes are always Pauli's. And Pauli's have +1 or -1 eigenvalue. So there's a very simple circuit, which is this one, which measures, using an ancilla, this parity check. So there's data here of which we want to measure the parity check. This is the plus state, superposition of 0 and 1. And this is a controlled P operator, which we can break down in smaller gates. And this is just Hadamard measuring in the Z basis, so this is also measuring in the X basis. Yeah, so an example, so for example, if P is x1, x2, x3, x4, then this is the controlled x1, x2, x3, x4. So depending on this control being 0 or 1, I have to apply all these x's. But you can perhaps understand that that's equivalent to having multiple C0 gates, right? That has the same action. Yeah? Because this does x1, this does x2, x3, x4, depending all if this qubit is 1. Yeah? So you can always break down this controlled P gate if you only have 2 qubit gates and not something acting on multiple qubits. You can always break this down into a bunch of 2 qubit gates. In fact, you can always break it down into some C0s or C phase gates. Now, there is a slight also modification. If you have P is all Z's, you can rewrite the circuit in this way. Let me see. Yes. Yeah, and I think I also mentioned this before, that this is really the workhorse of error correction. So, of course, if I do this circuit via 4 noisy C0 gauge, each with a fidelity perhaps 99%, which is amazingly good, but still these errors, they may add, right? So each gate has fidelity 99% and would add to this ancilla coming out not correctly if I measure it. Or worse, and I will discuss this in a moment, there may be errors that feed back to the data if this circuit is done imperfectly. And those errors that feed back to the data could actually defeat the whole purpose of doing error correction. But we'll show this in a moment. Okay, so I think I'll come to the Steen code a little bit later, so skip that for now. Now, so in some of the, so there are constructions for making stabilizer codes, and there is a very nice construction which is called the CSS construction, Kelderbank, Shor, Steen, which constructs stabilizer codes from classical codes. Classical linear binary codes, of which there are many. If you have two, you have 1 or 2 codes obeying certain properties, you can make a stabilizer code. But there are other ways of making, there are many ways of making stabilizer codes. Now you want to say, okay, so I can have a code family, or I can have a code family where I have some parameters like this Bacon-Shor family or the surface code family, which I can let the number of qubits grow and I can look at its properties. And perhaps I could use such a code to build a fault-tolerant quantum computer. But there's another route towards a fault-tolerant quantum computer that I'd like to stress in this lecture or in these lectures, which was developed in detail a bit earlier than the surface code idea, this topological code idea, and also has, it's basically the same as this von Neumann idea mentioned at the beginning, and it's using code concatenation. Okay, so now, okay, so the first comment I want to make is something like this. So I set a, so don't look too much at the slide because I want to sort of go beyond it. So a code with distance d can correct t errors. Now, first I'm going to assume that my parity check measurements are perfect. And let's say I have encoded my data. And so on the encoded data, this is maybe very small, there are possible errors. Okay, maybe I shouldn't draw this, etc. So I've encoded my data, say I've made a logical 0. And these are sitting there, and I assume there's a certain error rate which sprinkles some errors on these data qubits, denoted by these things. I do a round of quantum error correction. For now, I'm assuming that this error correction, these parity check measurements are done perfectly. And then I have another round of errors happening, and I do quantum error correction. I could also look at this as sort of a channel, but I only would do it once, in which I say, well, these data are sent through a channel, a noisy channel, which corrupts the data a little bit, and then I have to do error correction after the channel, and assuming that error correction is perfect. So how many bits can I get through the channel, or how many qubits can I get through the channel, depending on the noise of the channel. Now, for a code that can correct t errors, you understand, so what we want to describe is, you say, okay, well, a code can correct t errors. Let's say this code, correct t errors. So any pattern of t errors less here is fine. It will be caught by my quantum error correction and will be removed. But some errors that happen here will not be fine, in particular if I have t plus 1 or higher errors. Okay, so let's imagine these are n qubits. So if I have this is a very sketchy, simple argument. So I could have, I could place t plus 1 errors among these n qubits. Yeah? And what is the probability for having t plus 1 errors? Let's say probability for error, and I'm not specifying whether it's a x or y or z error, but let's imagine that the probability for an error on a single qubit is p. Yeah. Then, so I would have the probability so for a single qubit I have error probability p. So the probability for t plus 1 error somewhere is p to the t plus 1, and it's like minus p and minus t minus 1. But let me throw this out. And of course, so I'm just going to calculate the probability. This is, I call the probability for a logical error. Logical error. So what I'm doing here is, this is also called p bar. Yeah? So the code can correct t errors. So t plus 1 errors or more are bad. What's the probability for those events? Okay, so there's a probability that there are t plus 1 errors, t plus 2, t plus 3, etc. What's the leading order term? That's what I'm doing here. I'm saying the probability for an error is p. And then the leading order term, well, I'm going to, I actually don't care whether there are further errors, so I can take this out. So, and I'm going to say this approximately. The point is that the logical error, all the incorrectable errors, that error probability will scale as p to the t plus 1 times some combinatorial factor, which relates to how many, where all I can place the errors. Okay, so what I want now is that this p over line, this logical error, is of course less than that. Yeah? And so, and I'm going to say for what p is this less. So, oops, p. So I say this is, this is a very approximate heuristic reason, but the reason I'm giving it to you, because this is basically how a noise threshold comes about. So now I say so when is this a crossover? When this is equal to p. Yeah. So this equality, so this should be p threshold, right? So we want the logical error to be less than p, but we say when does it cross over? When is it equal to p, right? And that number I call the critical error rate, or the threshold error probability. Right, so you see c to the p to the t is 1. So that's that kind of thing gives you, yes, what I want to do with this, well, not much more. So this is the equation, rough form, for the threshold error, the threshold probability. Yes, what do I want to say next? So the idea is that if your probability p is less than pc, then it will mean that p is less than p. And you see how it scales. The logical error rate will scale kind of like pc to the t plus 1. Now if I use a code that can correct one error, t is 1. So for a code that can correct one error, p is something like a constant times p squared. So that's the improvement. This kind of thing is the improvement that you get from coding at a high price, because the thing that you have to do looks much more complicated. But then you can imagine, perhaps, maybe I should erase a few things, that if you could keep on doing this. So this is the idea of concatenation. So let's imagine I have my a code that can correct a single error. So it's the Shor code or the Steen code. If I do my quantum error correction, it will reduce the error rate, the logical error rate. It will be of order a constant times p squared. So that's nice, but that's not going to give me a fault-tolerant quantum computer. What I want to show is that I can get this logical error rate to be arbitrarily small at the price of adding more coding, more redundancy. Now, intuitively, the way you could do this is by recursively applying this. And I think I should erase a few things. So in some sense, I'd say, well, okay. Okay, so I want to make you familiar with two ideas. One is the simple idea of code concatenation. I could take a code like the 7-qubit code. So I have mapped 1 qubit onto 7 qubit, right? Now I could take every one of those 7 qubit. I could again map it onto 7 qubits. Yeah? And so now I have a 49 qubit code. So I encode 1 qubit in 49. Now I want to know what are the properties of this 49 qubit code. Yeah? Okay, so if I have two codes, let's say I do it not for two codes, both encoding 1 qubit with distance d1 and distance d2. So in total in the new code I'll have n1 times n2 qubits, where n1 and n2 were the number of qubits of my original code. And my distance gets multiplied. Right? Why is this the case? It's because let's imagine for this code I had the logical z. So let's say it's weight 3. Let's say it's z1, z2, z3. I don't know what code I'm talking about. And now when I do the concatenation, I say, well, every one of these, if I have z1 on this qubit, now I have to replace it by the logical z1 of this block. So this, where this is the logical z1 of the code I'm using here. So I have a code here, c1, and I have a code c2. This had weight 3, which was the distance of, say, d1. And now every one of those guys will be replaced by an object that has distance d2. So that gets multiplied. So the new, well, you can just verify this for yourself. Is this clear? People look a little puzzled, maybe. So the weight of the logicals, you just, instead of, if I replace every elementary qubit by a block of 7 qubits, then the z operator that acts there, I just replace by the logical z of those 7 qubits, which maybe acts on 3 qubits in this block. Now, if you look at, you could similar do, if I look at this code, so it's 1 in 49, say, if I were to use the 7-qubit code twice, I could look at that as one big code, which has parity checks. Now, these parity checks, they will also increase in weight. For example, if I had a code, original code which had parity check z1, z2, so c1 had a parity check, say, on these 2 qubits. Then now I have to replace z1, z2 by the logical z1, z2 of this code. And if that logical z1 had weight 3, then it will be weight 6. So it also increases. So that means it's a more complicated to measure these parity checks. So, but there's actually, so you could say, well, I can look at it as one big code and measure those parity checks, but actually that's not how you deal with it, because it is nicer to do this in a hierarchical fashion, in the following sense. So that's that leads me to this, and I'll illustrate that with an example. So maybe I can get you the example first. Okay, so let's imagine we use the So let's imagine we were using the bit flip code. And I was measuring this in the x basis, or mx. Okay, so let's imagine I want to do this. I'm using I'm using the, well, it depends on how you call top to bottom. Okay, I'm using the bit flip code. So I mapped, this is my 3 qubits, 3-bit repetition code. And this is a circuit that does error correction. Now, I want to concatenate this code to something else. So every one of those guys, I want to represent by a whole block of, say, 7 qubits. 3, 4, 5, 6, 7, it doesn't matter. So, and these are all blocks. And now I also, you see, there's also, so this now is this C phase gate will act between 2 blocks of 7. So the C phase gate of this code will be mapped onto a logical C phase gate of the 7-qubit code. Now, the way I want to do that, I could say, okay, that's the logical C phase, that's another logical C phase. This is a preparation of a logical ancilla for the 7-qubit code. But I've done this replacement step, but I also need to insert error correction. So the rule is this. Let's imagine I have a gate like this C phase here that I have to do. And then you say I'm going to have a replacement rule. So let's say I encode every one of those with now 7 qubits. I'm not drawing exactly 7. And then I want to do the sort of logical C phase. C phase. And I have to do so this is a unit that will get replaced by this unit. What is this unit? It's the unit which does the C phase at the logical level, and afterwards, and it actually doesn't depend so much whether I do it afterwards or forward. This is some technical things. I do quantum error correction on these 7 qubits. So this was a 7-qubit code. So the 7-qubit code has certain parity check operators, and I'm measuring them here. And so that's the replacement step. And this is denoted sort of like here. This goes after this. Now, I do need to be a bit careful. Okay, so similarly, if I have, say, the preparation, or let's say a measurement, here I had to measure, well, I could put a Hadamard here, maybe make it simpler. Hadamard measure in the Z basis. Let's say here there was 1 qubit that had to be measured in the Z basis. Now, how does that get mapped onto that unit? That will just get mapped onto measuring everybody in the Z basis, plus error correction, classical error correction. So I have and determining the value of the logical Z. So the point is that I replace this measurement of a single qubit by measuring all the qubits in my block, again in the Z basis. That will tell me the value of the logical Z, but of course there may be X errors that have happened that change this value. So with this data, I've measured all my qubits. if I do a parity check measurement, I only measured some information. Here I've measured all my qubits, so I have a lot of information. I have all the information about X errors that I want, and I can use that to determine the eigenvalue of the logical Z in a stable way. So what I do here is I do error correction and determine the logical, yeah? So I have to, if I don't do any error correction here, then this eigenvalue is possibly flipped by, you know, a little X error happening here. So I want to take that into account. So that, yes. So now, if I say logical C phase, there is a condition that that kind of unit has to obey. Because let's imagine I use my 7-qubit code not in context. I start with my 7-qubit code. So I had 2 qubits. I had this unit. Yeah. Maybe it came from some other code already, or maybe I just was starting at the base circuit. And I'm replacing those with the 7 qubits of the 7-qubit code. Now let's imagine in this logical, this is a big box. You have to specify what happens in this box. But let's imagine there is an error here, some error here, that is able to feed out and become 2 errors here. Or maybe, yes. So it could be, of course, an error here maps onto 1 error in this block and 1 error in that block. Well, that would be fine, because I have quantum error correction going on here. And the code can correct a single error. So if a single error somehow in this box propagates to become a single error here and possibly a single error there, I'm fine. Right? Because I do quantum error correction here, assuming there are no more errors, it will be corrected and there are no errors at the output. But what is bad is that if a single error here becomes 2 errors here. Because this single error is an order P event, and it becomes an event that I can correct. So I don't have this, I had this scaling where I say the logical error rate is constant times P squared for this code. So what I want is the idea is that you say, this has a basic error rate. Now I replace this with a new unit that has a logical error rate, which is lower. So I have to be careful in designing this. Yeah. And there are certain designs, like transversal gates, for which are very nice, for which errors do not propagate in a bad manner. So for example, and I think, let's see, is it what I want to? Yes. So what is it? Oh, man. So what's a transversal gate? So let's imagine, and there is, I think I have this in the exercise to show this, when the gate is transversal for a stabilizer code. So let's imagine I have these, so these are these 7 qubits, they're not 7 qubits, but let's imagine I do want to do a C0 gate. And a transversal C0 is a gate by which so there's 7 guys here, there's 7 guys there, maybe not what I drew, but I pair the first here, the first there, and I do the C0, and I pair the second here, the second there, and I do the C0, etc. Yeah? And why is this good? It's because, well, okay, so a single error happens here. Maybe this C0 gate fails, meaning that there's an error here and an error there. But it's never true that the because these qubits amongst each other, they don't talk to each other, right? So it's not possible for an error here to spread to any of the other qubits in this block, right? This qubit only talks to this guy, and that qubit talks to that guy, but among each other, there's no interaction. There's no 2-qubit gates. Yeah? So this type of way of doing a C0 gate is fault tolerant. Order 1 event, or order P events, single qubit errors do never become 2 errors in a block. if you have a code that can correct more errors, let's say it can correct t errors, what you want is that any errors of order less than t should never become, errors of order higher than t, right? Because those are incorrectable. And for that, you need to design your circuits in a subtle way. Okay, so what's... Yes. And so I have also in the exercise a... there is a way of measuring the parity checks for the Steen code. Okay, maybe I shouldn't say this. Okay, so there is an exercise that relates to this. Because there is a 513 code. So there's a code which is very small. It codes 1 qubit into 5. But it's much harder to do a controlled NOT gate for this code in this fault-tolerant rate. It doesn't have a transversal C0. And that's what. And then if you calculate the noise threshold, this noise threshold turns out to be not very good. So you concatenate this code with itself, and you can try to calculate the noise threshold for this scheme. And you use then, in terms of determining this noise threshold, you use the way you do the C0. And you see if the C0 is transversal, it's a very shallow circuit. It's a one-step circuit, right? You just do all these things at the same time. A more complicated circuit would use ancillas. The ancillas have to be verified. There are many, so it becomes a very complicated circuit, which means that if I have to look at where single errors can happen, well, there are many places which it can happen. So, in the noise threshold, I said P scales like a constant times, say, P squared, if I use a code and correct the signal error. And this was a combinatorial factor that's coming from where two pairs of two errors can happen that become two errors in a block that I can't correct. That combinatorial factor is going to be large when I use a very complicated construction for doing logic. Yeah? So this is an aspect that so the first, and so if you look at the area of fault-tolerant computation, the threshold theorem that one obtains through concatenation was sort of the earliest. Well, surface code were also very early, but in a sort of slightly different. So the threshold theorem was a fairly early realization, and then people started to calculate what is the value of the threshold for these concatenated codes, like concatenated 713. I'll show you some numbers, and they were not very good, order 10 to the minus 5. So meaning that in a model where your error rate or every qubit has to be at least, it has to be lower than 10 to the minus 5 in order for you to benefit from using error correction. A benefit meaning that the logical error rate is lower, and if you keep on concatenating, it gets lower and lower and lower. Okay, so the best scheme actually that it uses concatenation is a concatenation of the 4-qubit code that I showed and a 6-qubit code, which has a numerical threshold that's still determined of about 3%. Now, I don't know, well, it's always hard to compare these numbers and so on, but the surface code has 1%. So this is about, at least numerically, it indicates a very, very high noise threshold. There are also analytical lower bounds, which are much lower. But this scheme is not currently, well, at least nobody is thinking about experimentally realizing this, although I think it would be interesting to actually study this a bit more, because of its high noise threshold. Okay, so now I want to give you that overview of the threshold theorem, because now I've put down some elements in how you may imagine that you get a logical error rate which goes down the more overhead you have, the more often you use a code. So let's imagine, we construct circuits. We have our basic circuits we want to run, want to do an quantum algorithm. We take every gate in that circuit, or preparation step, or idling step, and we replace it by a new unit. And that new unit X, every qubit is replaced by, say, 7 qubits or 9 qubits. And we have a fault-tolerant realization of the gate plus an error correction step happening on those blocks or 7 or 9. Yeah? And then we look at this circuit and we say, okay, this is composed of 2-qubit gates and single qubit gates on these qubits on this block of 7 and so on. And we repeat that, right? So for those little elementary gates in that circuit, we again replace it by a 2-qubit gate by 2 blocks of 7 and the fault-tolerant version of the gate that you're looking at and an error correction step. That's the idea of concatenation at this computational level. Now, what happens when you do that? Okay, so every time, so let's say I have some unit like this, and every time it gets replaced by a new bigger unit which has S components, meaning that there are S single and 2-qubit gates in this whole thing, right? I'm not showing them here because I have to specify what E means. E is quantum error correction step. So I can write that as a circuit with the 2-qubit and single qubit gates. Yeah, so every time I do a concatenation step, one component gets replaced by S. So if I do that R times, I have a circuit with size scaling with S to the R. Now what happens with my error rate when I do this? Yeah. So I said that every time I do a concatenation step, my error rate squares, right? So well, there's some factor C, but it doesn't matter. So if I do R of those, I will have an error rate per component which scales like P to the 2 to the R. And let me call that epsilon. Now the important point, and this is why this kind of thing works, is that you see that the size of the total thing I'm doing is scales like S to the R, exponential with R, but the logical error rate scales doubly exponential, P to the 2 to the R. Yeah? Okay, so if I do R levels of concatenation, I get a circuit where every unit, every component has error rate epsilon. Now, I want to do some computation with this. And let's imagine I want to do a computation with, I want to run some short factoring algorithm which has n of those units. So where n is some polynomial, the number of qubits. Like, the Shor's algorithm has, this capital N scales like n to the third, where n, little n to the third, where n is the number of qubits I use. So, but I need to, so I want to take my Shor algorithm, and I want to encode it, and I want to know how much overhead that costs. Yeah? Okay, so my original circuit unencoded had size n. There were n components. Now, every component I'm going to do with error rate epsilon. Well, if epsilon is too small, then of course at the end, if I run the whole thing, it's going to produce nonsense. So I need to get an overall accuracy. The overall accuracy scales like roughly n times epsilon, right? Because errors just add. This component is wrong, this component is wrong. So I say that roughly scales with n times epsilon. And that needs to be some constant, right? I want to run my source factoring algorithm so that with probability 3/4, the whole algorithm produces the right answer. So that's my delta. Okay, so now when I put these numbers, so I put in this number, I'm not going to put in these things. And so the claim is then that I started with a circuit which was unencoded, which has n components. I end up with a fault-tolerant circuit with n, some constants depending on other numbers, n times log n to the log s, and s is some constant. Yeah? So this is called a polylogarithmic overhead. So this is the threshold theorem that says you can do fault-tolerant computation with polylogarithmic overhead. And this overhead also depends on the accuracy you want, of course, and it depends on the code you use, and depends on the error rate that you start with, whether you have to be below threshold. Yeah? Okay, but so that's a very nice, beautiful theorem. But then indeed the question is what does it imply? Is that the way we want to go? Yeah? for real code. So now I want to show you. So so we did some analysis way back when about, for example, if we take the 7-qubit code and you concatenate it with itself. And we do this in a 2-dimensional architecture. So my point here is that you can do also concatenation in 1D thing, right? What you need to do for that is you need to, you know, if qubits have to interact, that are not nearest neighbors in the way you've laid them out, you have to move them. Now, how you can move qubits is you say, well, I have ancilla qubits, which are sort of dummy states. I don't care their states, and I just swap those qubits around. So I can have this qubit here and that qubit there, and I here have dummy qubits, and I'm just swapping these guys, and then I swap this guy, and then I swap that guy, you know, and then I get this qubit over there, and then I do my 2-qubit gate, and then I swap this back. It doesn't make things faster, but you can show that you can do this all in a fault-tolerant manner. So we have here a unit cell where you can't probably see this, but so this is a unit cell. What is it actually? Oh, you can't really read it, how many qubits these are. But so this is, every point here denotes a qubit, and some of these O's are dummy qubits used for moving. And there are some D1 to D7, which are the data qubits. So those are the 7 qubits in my 7-qubit code. Then there's some guys there and some ancillas. And so this thing is 1 unit cell, and then you can kind of repeat this. Yeah? So the idea is that you break down all steps into purely local steps. And every time you do a step at a higher level, after that you do a quantum error correction step at the lower level. Yeah? So to be protected. So we, for example, estimated, so there was an analysis that, for example, for the concatenated 713 code, the threshold, this P critical is 3 times 10 to the minus 5. And we estimated that this noise threshold for this 2D setting, assuming that this noisy swap gates had the same error rate as other 2-qubit gates, we had to assume that the memory error rate of a tenth of the gate error was, actually, do I mix these things up? Was slightly different. No, I think I mixed something up here. Oh no, okay, that's fine. Yeah, so it was a slightly lower, but not that much lower. Of course, these kind of numbers depend on what you put in, right? Do you treat memory error as 1/10 of a gate error, or you treat it higher? How much is the noisy swap cost? If you have an architecture by which you can actually move qubits over some distance, you may not need this, right? Okay, so now I think in one of the previous lectures I also said I wanted to point out things where classical codes are different from quantum codes. And one obvious thing is in the construction of logic. Because in this von Neumann scheme, if you use the classical repetition code, all the gates, the Toffoli gate, you know what the Toffoli gate is? So that's this is the Toffoli gate, which says if these qubits are 1, this bit is flipped, and other circumstances this is not flipped. That's a gate that is sufficient to do classical computation with. And that can be done transversely. But you can prove that for stabilizer codes, and there's even more general theorems, that not all gates can be done transversely. Now, transversal gates are just one type of constructions, because you can imagine that for some codes, I can give you examples of this, you can do, if you do some gates, you're not exactly doing the logical C0, but you're doing the logical C0 modulo some permutation of qubits. That's fairly harmless, right? Because I can just imagine, okay, those qubits were permuted. Now that I know that, I don't need to do anything. So that's okay. There's other ways of doing gates. by code deformation. That's this technique that's used in the surface code. And there's also a lot of development on switching codes by gate switching. This relates to subsystem codes. I have to make some decisions about what I'm going to cover now, because we don't have too much time. Okay, so I want to talk now, the last 50 minutes, a little bit about indeed how to do gates fault tolerantly for stabilizer codes. And I want to also point out this special group played by the Clifford group of gates. So do you know what Clifford gates are? Is this, yeah? Okay, some. I have to see how far we get with this. I don't want to end in the middle of everything. Okay, so let's see. Are there questions at the moment? Okay, so what are the logical gates I need to do? This is, of course, the first question. What is a universal set of gates? And there are possible choices. And one choice is, for example, if you can do the Hadamard gate and the Toffoli gate, you can do universal quantum computation. So the Toffoli gate is universal for classical computation, but apparently you just need the Hadamard gate to get quantum computation. Okay, so one favorite set, but like I say, it's not unique, is if you can do Hadamard gate, single qubit Hadamard, the C0 gate, and the T gate. So the T gate is also a pi over 8 Z rotation, but you can also write it like this. And there's also an S gate, which I don't need, but I just want to write it because T squared is equal to S. Okay, so now there is a very important class of gates, and it's particularly important for stabilizer codes, which are the Clifford gates. So what is the property of the Clifford gates? Is that if a gate is a Clifford gate, then it has this property. U Clifford is a Clifford gate, and P is some Pauli operator acting on a variety, many qubits. And this said, if I let the Clifford gate act, by conjugation, I get another Pauli operator. And the point is that if you can only do Clifford gates, you can always classically simulate the whole circuit. This is called the Knill-Gottesman theorem. So the problem is, so it means that if I start, I try to make my quantum computer, I can only do Clifford gates, then it doesn't have any additional power. We cannot do factoring, we cannot do anything, we can classically simulate whatever we have. Now, what are Clifford gates? So Hadamard is a Clifford gate, because Hadamard on X is Z, right? That's a Pauli. The C0 gate is a Clifford gate. But the T gate is not a Clifford gate. So, and it turns out that it's much easier to have nice fault-tolerant constructions for Clifford gates than for the T gate, for stabilizer codes. It's not surprising, perhaps, because these Clifford gates have very simple actions on Pauli operators. So they have simple actions on the stabilizer. So for example, if I have a code, okay, so let's say I have a stabilizer code, S. So I can show you when the Hadamard is transversal. It's a very simple observation. Let's say I have a stabilizer code S, which is has two parts. And the first part are all the X parity checks, and the second part are all the Z parity checks. For example, S is this trivial, actually this is not such a good example, but anyhow. So my 4-qubit code, has one X check and one Z check, and they're the same. Yeah? So what I mean, this is S1, X and Z checks are the same. The 7-qubit code is another example. For the 7-qubit code, the X checks are also the same as the Z checks. Now, if such a code encodes a single qubit is encoded, say, which is not the case for that code, because it encodes 2-qubit. But let's imagine a single qubit is coded. So for example, the prime example is the 713 code. Still haven't written down its parity checks and so on. Then it's very simple to do the Hadamard. Because, okay, so how do you check that a gate is transversal? So how do I want to do a Hadamard, a logical Hadamard on these 7 qubits? 4, 5, 6, 7. I want to do it by doing, oh, it doesn't fit. Okay. By doing Hadamards on every one of them. How many I have? This 3, 4. So this is a simple. I have my 7 qubits here, and I want to do a logical Hadamard, and it would be nice if I can do it by doing a Hadamard on every one of the qubits. Yeah. Now, how do I decide whether this is a logical Hadamard or not? Well, first I want to see how doing this affects the stabilizer. Because it could be that if I do this to my stabilizer check, I get a new code. Now, then it's like more code deformation. Then I have to somehow get back to my old code if I want to keep on using this. If I want to connect that block to some other qubits, or I keep my new code, that's also fine, but maybe I have to repair it. Okay, so how does the Hadamards affect these stabilizer checks? Well, it's actually very simple. If the X checks are the same as the Z checks, the Hadamard just maps an X on a Z, right? So it just interchanges the X and the Z checks, and the code stays the same. So you can simply see it here. Now, the other thing, it has to be a Hadamard gate. It has to be a logical Hadamard gate. So I have to check that if I have a logical X, how is that logical Hadamard affecting it? Well, I write the logical X in terms of the what it does on the 7 qubits. Turns out that the logical X for my Steen code, so that's 713, my logical X is X2, X4, X6. And my logical Z is Z2, Z4, Z6. Oh, that looks nice. So I just have to apply Hadamard on 7 qubits on this thing, and you see that these X2, X4, X6 just get mapped onto Z2, Z4, Z6. Okay, so my argument is for any code for which the X checks act on the same qubits as the Z checks, my Hadamard is always transversal. That's a very simple fact. One can also show, and you're going to do that in the exercise, that so if I have a stabilizer, let's imagine I have a stabilizer for which I have separately X checks and Z checks, but they're not necessarily the same. They don't necessarily act on the same qubits in the same way. So it's a little bit more general. So you can show that the C naught is transversal. So that includes a wide variety of codes. For example, the surface code. So that's an exercise to actually look at that. So you can also look. This was, I think, in Gottesman's PhD thesis. This was originally. Okay, so where we are with time. Now, okay, so let's say the Hadamard and the C-NOT gate may not give us some trouble. Although, of course, the fact that if a C-NOT gate's transversal doesn't mean that you can do it in some 2D geometry in an easy way, right? For the surface code, we do this not in this transversal way. We do it differently. We do it by a trick called code deformation, which I will talk about in Sweden. Now, what about the T-gate? So the T-gate is trouble. Well, trouble. So there are stabilizer codes which have a special symmetry which makes them have a transversal T-gate. That's, for example, a 51.3 code. And there are code families that are being constructed. There's a lot of work that's going on in this area right now. But there's also a theorem, and this is a theorem about two-dimensional stabilizer codes. So it's not about concatenated codes. It's about a theorem about I lay out my qubits on a two-dimensional array, and my parity checks are always local on this array. That one can do only Clifford gates via constant depth or transversal code constructions. So there is a way of doing this transversal T-gate in three-dimensional surface. It's a three-dimensional code. And then you have to do some more work to do the Hadamard, but you have to go to 3 dimensions. So they're starting to get some no-go theorems that show that well, you can use topology and you know, but if you restrict yourself to 2D, it's limited in terms of what logic you can get, or you have to really work hard at it. So we have to distinguish that from the picture of concatenate. You could always use a concatenated code, even in 1 dimension, and make everything local. But then the noise threshold is bad, at least what we've seen so far. This Knill scheme is an exception. Or you could go for topological codes, but then in 2D, you have a lot of trouble to making this T-gate. Well, a lot of trouble. It's a huge overhead. And people are working on bringing this overhead down. So the current, one of the current ideas to do a T-gate is to use an ancilla. So there are some circuits. I mean, I have to stop very soon. So this is a circuit. So I have here a state in which I want to do a T-gate. Not at an encoded level, just at the logical level. So at the outcome of the circuit, I want to have T psi. And the way I can do this is with an ancilla. And the ancilla is here. 0, Hadamard, so that's a plus. And then on that plus, I apply a T. So let's assume I can make that ancilla somewhere, some ways. And then you see this is a controlled NOT gate. This is measuring the Z basis. And this is doing, depending on the measurement outcome, I do either nothing or I do the gate Sx. And S is this gate, which is also actually a Clifford gate. The point is, this circuit reduces doing the T gate to preparing ancilla and doing Clifford gates. So let's imagine that my Clifford gates are easy. I have tricks for them. Either it's transversal, or by code deformation. I can do that in the surface code. So then I say, oh, well, I just need to make these ancillas. Now I need to make them at an encoded level. So this is just this is a single qubit ancilla, but this has to be an encoded ancilla. So there are ideas that prepare many noisy ancilla, encoded ancillas, distill them, make fewer noiseless ancillas, and then feed them into this. And these kind of constructions have large overheads in terms of the gate. So what I want to point out here, but this is an ongoing subject. So here, for example, a single T gate requires hundreds of noiseless T ancillas, which are distilled into one. So there's still ongoing work to see if we can get a very plausible, well, I don't know. I don't know what you're willing to tolerate, but I think it's quite challenging to do the T gates this way. So I think to conclude, I want to make 2 points. To me, but this is a personal perspective you may absolutely disagree with. To me, the idea of if okay, so I don't know whether we have a chance of making a quantum computer. I think it's way harder than we think, and that doesn't matter. We should still try it. But I see sort of 2 stages if we want to go use this stabilizer code. One stage in which we make a memory, or quantum memory plus, which means that we just try to encode qubits in logical qubits and keep them that way, and do Clifford gates. But like I said, Clifford gates can be classically simulated, so we have no interesting computational power. We can't impress the NSA with what we can compute. In some sense, it's completely trivial. It's just like one step above classical stuff, right? Because what we prepare, so we prepare a logical 0, we have a logical plus, and we do a few Clifford gates. So, but then we have our error correction machinery there. We show we're below threshold, so it's very, very non-trivial to get there. And then the next step up is to do actual logic and also realize this T-gate. So there are 2 things that then play a role. One is that requires either ancilla factories or different schemes. And secondly, it also implies the algorithms that process the error information need to be sufficiently fast. And I have not had time to discuss this. And if you're interested in thinking about this, I have put in my review some simple arguments. I don't think it's a showstopper, but I think it's just a word of caution, in which I sort of argue this. So let's imagine we do a surface code-based quantum computation, and we do a T-gate using what's called now magic state distillation and injection and so on. And there's some decoder, there's some way in which we process the error information all the time. And let's say our process is the rate at which syndrome bits are processed, and our generate is the rate at which syndrome bits are generated. And so we have some 2-dimensional layout, and from this layout there's some I/O with our quantum substrate, and there's bits being generated all the time, and there is maybe perhaps local cells that are communicating that process these syndrome, these parity check bits. But let's assume that the rate at which we generate it is higher than the rate at which we process it. Now, then of course you say, well, then we're going to be running behind. Right? There's a sort of a backlog of syndrome data that is accumulating that I haven't dealt with. Now, I claim for a quantum memory, this is not a problem. For a quantum memory, well, all you have to do is you just have to let these, you have to collect all this parity check information, and at the end of the day, you measure perhaps all the qubits, and then you're going to go home, and the next day you're all fresh, and you're going to process your syndrome data. And you're going to finally interpret what that measurement at the end meant. Yeah? But if you do fault-tolerant logic, you can't do that. You have to know whether logical Pauli errors haven't happened on the data. And the reason is that you cannot, so this goes, let's see. So the reason is that these logical so if you have a T-gate, so T-gate's not a Clifford gate. So if a logical Pauli happened on your data before you did the T-gate, then, and you only learn about that later, then, it is equivalent, let's see. So xt, I say, oh, well, I want to write it. So I first have x done. Well, maybe I want to write, okay, so I first have, I'm writing this in terms of, okay, so I have x, I have t. So I have my data coming in here. Some logical Pauli happened. I was not aware of it because I haven't been looking at the syndrome bits because I was still dealing with syndrome bits from way earlier in the computation. I am doing a T-gate. Now, I want to relate now later I learned that the logical Pauli happened here. Yeah? So then I say, well, I want this to be equivalent to first a T-gate and then something else. Well, what is it equal to? It's T dagger x T. Right? I just insert T dagger here. So this is equivalent to first doing the T-gate and then doing this, T dagger xt. This is proportional to Sx, or something. It's a Clifford gate. So this thing, you see T dagger xt is conjugating a Pauli with a Clifford, which is not a Pauli because the T is not in the Clifford group. So this is some Clifford error. So now, this whatever happened was equivalent doing the T-gate on time without logical Paulis and then having a Clifford error. You say, oh my God, I went way further in the computation. A Clifford error happened, and I have to see what happens with the Clifford errors in the next gates that I've done. And the problem will continue to spread. Yeah? So what you need to do, you see, okay, I'm here in time. I want to do my T-gate, but I have not done processing my parity check record yet. And there could have been a logical Pauli that happened. So, okay, hold the computation. We're going to stop. We're going to first process the parity check record in order to determine whether there's a logical Pauli has happened. No? During that time that you're stopped, what happens? Well, you're going to have a further backlog because the rate at which you're processing your bits is slower than the rate at which you're generating them. This is assumption, right? I'm not saying this is the case practically. So what you can argue, which I do in this review, every time you hit this T-gate, you have to wait until you're done. And while you're waiting, new stuff's happening. So the next time you do a T-gate, you have to wait for longer. And this keeps on happening. So the point is, if you have a polynomial number of T-gates, you actually, at the last T-gate, you will have to wait a time that scales exponentially in n. That shows, so that's bad, right? It would show that quantum computation is not, so I really like people to tell me this is not, I don't think this is going to happen. I think there are arguments that save you from this. At least this assumption that this is the case is a bit too simple. But what it shows is that your decoder, this processing of this error information has to be fast and not get into this backlog problem. And that's not an issue for memory. So that's why I see that as somewhat, of higher complexity. I'm also happy if you disagree with me with this argument or you have questions about it, because it's just I thought I formulated it in this review, and I hope to, well, okay, so I hope that, it generates the discussion, because you can ask, is this assumption correct? Yeah? And you have to show that your processing can be done in a time that doesn't depend on the code distance. Why? Well, if I want to do a long computation, I need a large code distance. And if the decoding rate is going to depend on my code distance, for some large enough code distance, I'm going to run in my backlog problem. Yeah? And so there's claims that indeed the decoding rate does not depend on the code distance, but this is a subtle thing, because it's actually the average decoding time does not depend on the code distance. But you have to, so this is not entirely settled, at least not settled to the extent that I'd like to see it settled. Okay, sorry I went over time. Questions? People are sort of, you can ask me questions also right after. Okay, well, I hope you enjoyed the school, and I think you all go to, oh, there's David, okay. You'll see each other in Delft pretty soon, I think in a month or so.